Now moving on from Euler's method, we're going to look at a more general form for what we call a second order Runge-Kutta method. And in this slide, we have the representation of the general form as indicated here. You'll notice that in this vector representation, again, y is represented as a vector, a multidimensional vector at time x plus h, or at position x plus h, can be obtained from the current position plus the following right-hand side terms. The first term actually is pretty much what we have for Euler's method, but now we're taking it a step farther and looking at another adjustment using the differential equation again. Again, remember the f vector here is a description of the first derivative and looking at a description of the ODE, and then we're using it again with another component times some constant C1, and noticing that we've moved the x to a particular farther distance down, let's say on the x-axis, but we've also shifted the y, and that almost, if you'll look at that carefully, almost looks like another Euler method step inside of it. So this is the form of what's called a second order Runge-Kutta method. This is what they generally look like, and they're separated by different values of what the C0, C1, P, and Q are. And we determine those by matching a Taylor series representation to this particular form. Now, because we're going to look at different ways of deriving looks for this particular equation, I've indicated this as indicated by this diamond pattern, so we'll call this the diamond equation. That again is the general form for the second order Runge-Kutta method. And we'll come back to it later as we find different ways of representing these terms. First thing we'll start off with is just remembering, looking at Taylor series expansions as we had before and stopping after the second derivative term. This is what we know to be true in terms of the Taylor series expansion for the vector y x at position x plus h. And again, we're truncating after this particular term here, so everything else would involve higher order terms, and the lowest order would be cubic, so we'll say that's plus O of h squared. But again, we're going to exploit the fact that, the derivative is actually given as part of the ODE. Remember that y prime, we're usually writing something like y prime equals f of x comma y. So, so in this particular case, we can rewrite this Taylor series expansion, and everywhere that we had y prime, we're going to put an f, all right? And in this particular case, instead of y double prime, notice we'll have the derivative of f there, evaluated x and y, again, y being a vector valued function. So all we've done is just used standard Taylor series expansion and exploited the ODE itself as a representation of the derivative. That's all we've done. Replaced y prime with the right-hand side of the ODE, f, and then if we had y double prime, it's going to be the derivative of f, and then if you had y triple prime, it would be the second derivative of f. Okay? So just keep that in mind in terms of representing what y of x plus h could be using the ODE itself. But if you go back to calculus, this probably would be third semester calculus, looking at vector representations of functions. If we wanted to describe what does that derivative of f look like, in other words, if we were representing the derivative of a multi-valued function f of x comma y, where y is a vector, then you could describe that derivative in terms of partial derivatives. And this is just going to calculus, multivariate calculus, to represent it. And that would be the definition of what the derivative would be. It would be the partial of f with respect to x, and then sum of all of the other partials of f with respect to each of the y components. And so it will be the partial of f with respect to y sub I times the derivative of y I, and summed up from 0 to n minus 1. But then again, we can exploit the fact that each one of these y primes, again, is just the right-hand side, the appropriate right-hand side, as if you have a system of first-order ODEs. If you only have one, then it's just f. But you could have several, because we know how to take a higher-order differential equation and describe it as a set of first orders. and that's why we index from 0 to n minus 1. So now we have a way of describing this derivative of the f using, again, the original ODE. All right? So what we have now is an expansion where we can now write y of x plus h is y of x plus this term f times h plus h squared times this representation of the derivative. Okay? Again, we go back to the previous slide. All we're trying to do now is fill in what this is right here. Okay? The other part we already have for Taylor series. Now we're describing what that derivative looks like with of f. Okay? And so this is the substitution that goes in. All right? So if we go back to the diamond equation, then what we've got to have here is we've got to have another way of looking at, well, how can we describe this term out of that method, this idea of how do you describe f when you've moved in x and you've moved in y in terms of these shifts of both x and y. And this turns out you can do this with, again, multivariate representations with Taylor series. So this is how Taylor series works in several variables. This is more complicated, but you can actually look at Taylor series expansions for multi-valued functions. This is a function of x and y, okay? Previous Taylor series expansions like we just did in this previous slide, if you go back to the previous slide, this is Taylor series just expanding in one dimension, x plus h. So what we're looking at now is how do you write Taylor series when you have two dimensions, in this case two parameters here. And this is what it looks like. Right? So it's a way of saying, well, if you want to advance in x and y, it's f where you currently are plus partials times h, and then you have qh times these partial derivatives here with respect to all the yi's times f of iy. So we have now a representation of that component of the second order Runge-Kutta method that involves, again, terms that come from the original ordinary differential equation. So, again, don't get freaked out. All we do now is just we can rewrite the original description of the of our second order Runge-Kutta method in this particular way now, which is really nice because it only involves things that we know. In other words, representations of the right-hand side now, and using the right-hand side again with now all these partial derivatives in there. So if you do the matching between this particular representation of the diamond and the star equation that we had earlier, you know, if you print this out and look at them, so if you compare this star equation with what we've now rewritten the diamond equation to be, then with a little algebra you can show that, well, we've actually shown there's some relationships between these constants that have to happen. That the sum of C0 and C1 have to be 1, that C1 times P has to be C1 times Q, and the products both have to be equal to a half. So these are the constraints now, using Taylor series expansions in 1 and 2 variables to produce constraints on the original representation of the second order Runge-Kutta method. So again, if we go back, we're just saying these particular constants here, C0 and C1, are not random, right? You can actually derive constraints on them based on exploiting Taylor series representations for functions of 1 and 2 variables. So popular choices are indicated here for the C's and the P's and the Q's, and the one we're going to focus on in this class for the rest of the chapter is sometimes called the modified Euler's method. The case that we don't have the C0 term is 0 and C1 is 1, so you can see that it's going to involve this term plus all of these partial derivatives, so to speak, of f with respect to x and with respect to all the yi's. Okay. So that is where we're at with modified Euler's method was one of those particular cases, and this is what the method looks like. If we just stare at the method just in terms of, again, looking at those constraints with the C's and the P and the P and the Q's, the C0 and C1, this is what modified Euler's method looks like. It looks like the original Euler's method up to this point of F times H, but then we add this term. So we evaluate the right-hand side of the ODE, shifted an x, h over 2, x, adding h over 2 to x, and then making a step with y as well. So we're shifting the y, and we're shifting the x, and then multiplying that times h. And you can see this term is going to be order h squared in general. If you think of this involving h's and this involving h's, and you're multiplying h, it's going to be an h squared term. But the graphical representation of this method is actually more powerful, that you can actually see how it might be a little bit more accurate than the original Euler's method as we integrate from x to x plus h. We'll return to the same sort of Cartesian representation we had before with Euler's method. Let's look at the x-axis here. We're trying to integrate from x to x plus h. We're drawing the derivative, not the function itself. Remember, it's an ODE, so it's a description of the derivative. The green curve here is f of xy. Right? So again, the ODE we're solving would be of the form something like, y prime of x is equal to, f of x comma y. So again, the green curve describes the derivative. And the goal technically would be to integrate, which would be trying to find the area under the curve from x to x plus h. So we could even sketch that in if we wanted to. We're trying to find all the area underneath that curve. The goal here is to not look at just evaluating f at at the x point and the corresponding y, because remember that's exactly what we did to get Euler's method. It would be the area here. That's what Euler method gets. So you can see clearly with this picture, we're not using that as the height of this rectangle. We're using this midpoint now. Some people, that's why sometimes this is called, modified Euler or midpoint method here, or there's midpoint method. So we go halfway into the interval. That's x plus h over 2, assuming the distance here from starting to finish is h. So we're going to the midpoint, and we're using that particular value on the green curve as the height of the rectangle. So you can see there's going to over-approximate in some cases and under-approximate in others, but together it's actually a lot more accurate than what we had with the original Euler method. The complexity is how do you describe this height? Okay, it's not just saying x, it's not just f of x plus h over 2 and y of h over 2. You have to have a representation for y being shifted to x plus h over 2, but we know how to do that. This is just represented basically as doing an Euler step, a very simple Euler step, but only a half step. So it's not you're not multiplying the right-hand side f by h, you just multiply by h over 2, and then we'll just rewrite that in this way of that's y of x plus this quantity k0 over 2. It's just to simplify the algorithm, okay? And so if we can produce that value, then this height of the rectangle would be this, f of x plus h over 2, comma y plus k0 over 2. That's the way to describe the top of this rectangle so that we can use that as our this times h as our estimate of the area under the curve, which is our estimate of integrating from x to x plus h. So it generally turns out to be much better than the standard Euler method, which again was the shaded area that I drew down there and highlighted at the bottom. In the next slide, we just use that same picture, but just to annotate it again. The difference here, remember that the area in the original Euler's method was proportional to the curvature, the idea here is the area of this panel is such that the area is proportional to the curvature. In other words, in this case, it'll be the second derivative of the first derivative, which will be the third derivative. So let me rephrase that. In Euler's method, that area was proportional basically to the slope, the derivative of the first derivative. Now, for the curvature, it's the second derivative of this function, which this f is the same thing as y prime of x. So that's why we're looking at it's proportional to the third derivative. Euler's method, it would be proportional, that area would be proportional to the second derivative, okay? So again, sometimes this is called, actually this is called Runge's midpoint method. It was proposed in 1895 as a better way of possibly integrating. Using information from the ODE, the f, the right-hand side, a little bit farther down the road than just at x, because it takes into account a little bit more of how this thing is curving, all right, around this midpoint than just using what we know at x. So it's a little bit more far looking down in terms of what the derivative is doing. Okay, so again, this is modified Euler's method, and it actually is computed in 2 steps, which we'll see in the next slide. So if we go to the next slide, you can see modified Euler's is this particular approach. You get the K0 term, you get an estimate of y at the midpoint by Euler's method. All right, so we get this by just h times the right-hand side, and then we go ahead and then approximate that new area, getting the area of the panel, so which is proportional to the curvature, and then update our solution. Okay, so that's how we move and integrate along the axis by getting the K0 term and the K1 term, as we illustrated graphically with the previous method. Very easy to implement and is generally more accurate than the original Euler's method. And for completeness purposes, there are higher order Runge-Kutta methods that take on this very similar type of approach that we did for the modified Euler's. And this is just an illustration of what the fourth order Runge-Kutta method looks like. I'm not going to derive it, but basically the advancement of y from x to x plus h takes on more evaluations of the right-hand side function. And this is just an indication of this looks like the standard Euler step we took before, and then sort of this is the modified Euler. So you can see sort of the modified Euler starting off, and then we're taking some other steps to continue on and look at different combinations, looking at different sampling of the right-hand side to get a better understanding of the curvature of the solution, and then using those sort of a weighted combination of all of those evaluations to give us a best estimate of what the area of the curve is. Determining the step size is usually by trial and error, though. You don't want it too large, but yet if it's too small, then you're taking many more evaluations than you wanted to. So, so it's just, it's just sort of a little bit of an art and science there. But we'll look just quickly at what this code in the Python looks like to do this Runge-Kutta method. Basically, again, the user has to be able to code up the f right-hand side that describes the set of first-order differential equations, and then the method's very simple to evaluate in terms of calling that function several times, producing the results, taking this sort of weighted average of it, and then updating your step. Okay. If we just take a quick look in the textbook of the Python code for the fourth-order Runge-Kutta method, this is what it looks like. Again, all the functions inside all these modules, the one that does the main work is called integrate. That's just the design. Again, you have to be careful when you're trying to use different integrate functions, so you have to load the modules at a time and make sure they're active while you're using them. But again, the user has to create a description of all the first order equations. There's only one if it's just a first order. If it's second or third or fourth order, if it involves the third derivative, you've got to produce a set of 3 first order equations and define that as f, capital F. Where do you want to start integrating? Where do you want to stop? And then you need an array for the particular solution values of y, and then what the step size is. So everything is pretty consistent like we had before. And then again, here's just an illustration of the method. It's about as simple as you can be. After the user has defined that function, the integration is just using the user's f in a sequence here to get these constants k0, k1, k3, k0 through k3, and then we just simply take the weighted combinations and return that step to update, and if we go back now, if we'll move forward again to look at the rest of the code, then you can see just starting off with two lists, we're just going to use list to produce all the values of moving x along the axis and then getting the corresponding y's. We're just going to call the Runge-Kutta method each time and then update x. We get the update for y, and we just keep iterating until we hit the final integration step, or the boundary of x stop, where we want to stop. And then we just convert the list to arrays and return those. So in the next lecture, what we'll do is we'll actually look at some examples now of how to use these methods to produce the numerical solution to initial value problems.